I'm gonna start recording here, but we will make sure that you're learning. So with that in mind, I think I was intending today I started drafting up this long math PowerPoint, and then I looked at it and was like, oh my goodness, like I am not gonna sit here for an hour of you guys' times and talk about math. So it's not this course. So I'm going to talk a little bit about solar energy because that is the main idea, and that's what this next little bit of information is going through. So, and like I said, by this weekend, I will have an answer for you for the remainder of this course. We're not too far along. It's only 8 days in. Hopefully the last 2 weeks in our meetings have been somewhat interesting and informative related to fossil fuels and the idea of how energy is created. But this weekend, I will have an answer for you for how we're going to deal with these math problems. So that is to come. But for now, I'm going to I want to touch on the math just for this week because I'm hoping that I can give you a general idea of why these problems are confusing. And then, yeah, so like I said, next week, this is going to be differently structured depending on what I hear from my supervisor, what he wants to do with this course. So, but you will have an answer this weekend. Does that sound good to everyone?
Yeah.
Okay, I will send an email
That's great.
I'll send an email to everyone today stating all this. And then, yes. So, okay, let me share my screen for what I have going on here. So, okay, so this is what I thought you were gonna get out of this course. And so at first I kind of just want to touch about solar energy and the basics of how it's created, right? Because I think people just see solar panels and they're like, okay, that's solar energy. And then they move on, right? Like, I don't think there's a lot of like intense conversation about like how it's working. So that's kind of the point of the slide. So on the right there, I just kind of found this document that showed definitions of key terms when talking about solar energy. And I think they're really, really important terms to note. So that's kind of why I have them written down here. So you might have heard the term solar photovoltaic before, or PV. But basically what that is that is referring to the solar panels. So solar panels are called solar PV panels. And basically it's the generation of electricity from the sun's energy using cells, or PV cells are just the panels that I'm referring to that are showed here. And basically the main idea here is that with solar panels, we're generating electricity, and we're doing that by taking heat energy or light energy. Heat and light energy are sometimes used interchangeably, but I think the proper term here is light energy. And we're ultimately converting it to electricity by converting it to electrical energy and converting the different type of electricity that we're using into its most useful form. So on this left here, you can see that this is kind of just a very basic definition of how solar energy is working. So essentially sunlight is hitting those panels, as you can see there. So we have the sun here, right? And it's hitting the panels. And what that's doing is it's causing your electrons to move and generate something called DC electricity. So I don't know if you have a big background in electricity, but basically, when we're talking about electricity, there's two different forms. There's DC and AC. So DC is called direct current. AC is called alternating current, and they're just denoted as DC or AC. And basically, if you don't know how electricity works, how we think about it, or how you might have done it if you in like middle school did these labs, is electricity works it's the flow of electrons. So that is the most basic definition of electricity, the flow of electrons. And in classes, in a lot of labs, like what people will do is they will have a conductor, which is typically like something like a copper wire, and basically mock electricity by connecting the wires and, having a battery or a load, so connecting the wire from one side of the battery to the other. And then when they touch both sides of the wires to both sides of the batteries, they might have a light bulb in the middle and the light bulb lights. And then if they take the wire away, the light bulb stops lighting. So basically, the whole point of that's just a circuit idea. I don't know if you really care about that, but basically the difference between DC and AC is DC is direct flow. So your electrons are only flowing in one way. Alternating current, your electrons are flowing various different ways, and they can go back and forth, and they have a lot of different directions that they can flow. And so the reason that I'm talking about all this is when we're talking about electricity that we use in modern day, we are talking about AC electricity. And again, AC is when we have, if we know electricity is a flow of electrons, AC is just a flow of electrons moving various different ways. And you can kind of think, assume why that is more beneficial than DC, right? I mean, DC is only going in one way. So obviously that's not as beneficial to us for society and for a lot of different technological applications as AC. So that's what the second half here, and this is why the second half is important. And it's that when we have solar panels hitting that, or sunlight hitting that solar panel and generating DC electricity, what they're doing is they're causing these electrons to start flowing, right? So that is what, on the most basic level, that is what solar energy is doing. And if we really dive into like the different components of a solar panel, we can see that silicone is often used. And the reason for that and the reason for all of the different components of the solar panel is they're all helping aid the flow of electrons, because the flow of electrons is creating electricity. And back to how this is all relating to energy, electrical energy basically is the primary form of energy for electricity. So I think of electricity almost as a secondary form of electricity. We can use or harness electrical energy to create electricity. So this is all of the cycle. This is, all these points are related, but all of this is coming back to we are using solar energy or light energy to convert it to electrical energy, to convert it to electricity. And the way we're all doing this is by, this concept right here. So again, this is kind of a more complicated definition of solar energy and how it works. But just know that when that the sun is hitting the panels here, it's creating electrons to move all different ways. And then there's a converter that happens. It's called an inverter that converts the DC to AC electricity. And that AC electricity is what we can harness and use in our homes and our businesses. So that is the main takeaway here. And so it's a fact that those three steps, just know that the sunlight hits the panel, electrons are moving all around. We have an inverter near the electric panel, and those convert the electricity forms, and then we can use it. So the other couple terms here that I just want to note the difference between. So a solar cell is a sandwich of two different layers of silicone. So I mentioned a minute ago that silicone is a primary material used in these cells and these panels. So it's two different layers of silicone that have been specially treated so they will let electricity through them in a specific way. So that makes sense, right? Because we know that all of this is relating to the fact that we are creating electricity that we can harness and use. So a solar panel is made up of many solar cells. As you can see here, we've got some panels. And then a solar array is a collection of multiple solar panels. So you might think of a solar array too as like a solar farm, which is typically how we use them in large scale applications as a solar farm. So just kind of note the difference there, that solar cell creates a solar panel, which creates a solar array. So I know that was a mouthful, but this really just kind of recognize that general diagram and how solar energy is created, and not just how solar energy is created, I guess, but how we're harnessing that solar energy in this second step here to create electrical energy to ultimately create electricity to use in our homes. So I think the main thing we're talking about solar energy is we have to talk about the pros and the cons, because there are a lot of pros and there are a lot of cons. And I think that this is a very exhaustive list of pros and cons. So I just want to kind of touch on a few that I think are most interesting and most important. And, if you have comments, feel free. It's a conversation, a lot of these pros and cons, how you feel. So for pros, obviously, right, it's using solar energy as a renewable form of energy. It's something that no matter what happens, we're always going to have the sun, at least in our lifetimes, right? So we're not going to run out of coal. We're not going to run out of, or we can run out of coal. We can run out of oil, but we can't run out of sunlight. So that is a huge pro of solar energy. So on top of that, it is literally sustainable, and that is true in the sense that once those solar panels are in like a field or in a farm, however you have your solar panels, they don't have much maintenance required. So with that being in mind, there's not much cost associated once those solar panels are in. And there's no huge concern that they're going to stop working, right? As long as we have areas that are in direct sunlight. So that's kind of what a lot of these good bullet points are referring to. So, they can be cheap, and that's because they're low maintenance. And that's a good point. The second one there, that we're only advancing further in technology. So they could only become cheaper if we figure out different materials to use that will substitute for silicone that are going to be cheaper. That's another way that it's a pro. The other thing I think that is a huge pro, that's a really interesting one that a lot of people might not think about, and it's the fact that it is effective and very effective in remote areas. And this is a huge thing that I think about a lot. And it's like the fact that we have these huge ways that we have to create energy right now, and it takes up a lot of space. Any form of energy that we create, or any way that we're creating energy and electricity for our use, it creates a ton of space, and modern, what we're doing right now, creates a ton of pollution. But with solar panels, they're effective in places where it's remote, right? So like things like burning coal and burning fossil fuels, we're not really doing those in the middle of the desert, right? I mean, there's not a lot of people, things like that. But for solar energy, remote areas are the most ideal place for them to be, because there's no buildings in the way blocking sunlight from hitting them. There's no people that can, go around them and tamper with them and try to impact them in a negative way. Like that's, I guess, a huge pro, in my opinion, for solar energy. And it's the fact that, like we can use land in areas that we don't have a use for land right now. So solar panels, I think, are very beneficial in that way. On top of that, something that that I talked a lot about in my solar and sustainable classes that I took in school, and it's the fact that installing them on rooftops is a great energy efficient thing to do for a lot of different ways. So one, it provides energy directly to the building below it that the roof is on, but also for a roof, like that's just unused space. I mean, we already destroyed the land to put the building. So I think putting solar panels on roofs is like a great idea, because there's nothing on a roof that's going to obstruct the sunlight, right? So that, I think, is another interesting thing to talk about. But now when talking about the cons, there's reasons that we don't have solar panels in every inch of the desert. And there's reasons we don't have them at every single rooftop. And so I think some of those cons kind of go into that. So to kind of touch on some of them, solar energy storage can be expensive. What that's referring to is going back to this. So, we have all these different components, and this harnessing of solar energy, and all of that is ultimately creating this electricity. But when we have farms like this, where's that electricity or energy going, right? I mean, there's no, it's not just going directly in most situations. Like when it's at farm like this, it's not going directly to homes and everything. So that storage of that energy until we use it is pretty expensive, or it can be. So the other thing that it's important to note here, so it has high upfront costs of solar panels. So back to this, like installing an inverter and creating these panels, and certainly creating these solar arrays, it's expensive, and it uses a lot of materials, and it uses a lot of land, in the sense that even this is in a desert, you can see, but like it's still destroying land of animals that are living there. And it's still negatively impacting like the natural land there, right? Which is like, if we kind of think about, I always think like in the forest, like in the Amazon, we're constantly destroying the trees there. This is kind of the same thing, but like it's like good. So it's like kind of a hard situation to balance there. Like we're using energy or we're creating and harnessing energy in a good, not creating, we're harnessing energy in a good way, but by doing so, we're destroying land. And like that, at what point are we just going to have to destroy all of our land? Because that's the other hard thing is with solar energy, it does create a lot of energy, but with the amount of solar panels we have right now, not enough to replace fossil fuels and the energy we get from fossil fuels. So is it worth it to have like just giant farms of solar panels like forever? And that's kind of con, right? So another interesting one that I'll talk a lot about when we talk about wind energy, but it's this idea that the actual production of solar panels can create significant pollution. And this is something that when talking about renewable energy is never really touched about. And this is kind of a big idea of sustainability. And it's this idea that it's a life cycle assessment. So what a life cycle assessment is doing is it's basically assessing the whole life of a material or of something like a solar panel. So from the creation to the disposal of it. And that is something that when talking about renewable energy should really be talked about, right? We should talk about this whole life cycle because it's even though the intermediate, so like after we created the solar panels, this intermediate period is great, right? Like we're have these farms and they're giving us electricity for our houses and it's not creating pollution or doing anything. But then let's say we have to tear up where those solar panels are to put more buildings or more houses or something. All of a sudden, the destruction of those solar panels, what are we going to do with all those random panels, right? Or when the panels burn out and go bad. And there's some studies or some, a lot of professors have looked into like the toxicity of solar panels after they burnt out. All of that might be significant pollution issues. And like this kind of saying, so like the initial production of solar panels definitely can create significant pollution in the sense that like we have to obviously, looking at this, we don't just pull these panels from the ground, right? We have to have processes and chemical reactions that are creating those. And those in itself are energy expensive and they use a lot of water and they require factories to create solar panels. So all of this is kind of showing you that it's not as simple as putting solar panels all around the world to combat the energy crisis. It's that there's reasons that it hasn't been done yet. So I just think that's important to note. Let's see, what other ones that are interesting to talk about here? So I think a big con, I don't really know if it's mentioned here, but another one that I think about a lot is the fact that it's not always beneficial to have solar panels in areas where you don't have a lot of sun. So that's another hard thing to think about. Obviously, and in areas where like there's lots of cities and high rises where we probably would want that extra energy. There's not a lot of places to put large amounts of solar panels. But so yeah, so as you can see, basically all this is just to show you that there's a lot of pros, there's a lot of cons, and there's reasons that a ton of people are for it, right? And then there's also reasons that it hasn't been done yet. So just to kind of think about it and put it into perspective, I think it's important to look at both sides of it. Okay, so really that's all I had for like the solar energy side of it. Kind of just wanted to provide a brief overview of what solar energy is and how we harness solar energy to ultimately create energy in the form that we can use it. So that's the main idea that I wanted you to get out of solar energy. I just, I think it's beneficial, like when people are talking about solar and solar energy, to be able to know a lot of these reasons for why and it's good and why it isn't being done yet. Knowing both sides is important. So okay, so kind of what I want to do is touch a little bit on the math questions for this week. Don't worry about doing them for now, but I would definitely do the chapter 3. There's a quiz. There's not a quiz for chapter 4. Please, for this week, I would suggest read chapter 3, read chapter 4, and do the questions on chapter 3 that are not the math questions. So there's a lot of questions that kind of deal with solar photovoltaics and things like that. So do the questions that are related to that. And then for the math questions, either yeah, just do that for now. You can just skip the math questions, don't answer it. I know it might tell you you have like a 20%, whatever it tells you, but I'll adjust it in GenNet. So I'll probably start putting your grades into GenNet or something. But like I said, this week we'll figure that out. But anyways, just to kind of touch on the math, I want to at least, if I'm not going to make you do the math, I want to touch on why it's complicated. So this is the biggest place to start because I think, especially in the reason I don't want to do the math is with all of you here, I don't think there were any math prerequisites for this course or engineering prerequisites for this course, which means we're all starting at various levels of understanding and backgrounds in energy and engineering, really. So that's kind of what these math questions are. So this is a really important document here. So, and we're kind of jumping ships here. So just bear with me for the remainder of the time here. But I don't know if you've ever seen a chart like this, but in science and in engineering, we use SI units. So this isn't things like inches. This isn't things like feet. Of course, in America, we use those and they really are not great units to use because there's no easy conversion to them. So when talking about like energy and like this course in the book, they are usually using SI units or converting things like feet and horsepower into SI units because they make a lot more sense. And this chart is showing why they make a lot more sense. So you've probably heard of things like kilogram, kilometer, kilometer, kilogram, kilometer. Oh, give me another one. You get the point. But basically, here we go. So there are different ways that we can denote, like, let me back up here. So I think the best way to think about this is we have things like milligrams and grams, right? So we're going to start talking about grams first because I think that's the easiest way. So everyone knows what a gram is. So, right, a gram is a unit of weight, right, or a unit of mass. So the gram is something that's called a base unit. But if we say a kilogram, that means it's just a gram times 1,000. So 1 gram or 1,000 grams is 1 kilogram. So, and it, I think the way I'm gonna, sorry, bear with me for a sec. I'm gonna pull up my iPad so I can start typing. So I think I'm probably confusing you for the first minute, but this is why we're not doing the math for this portion. Sorry, bear with me for a minute. Pulling up my iPad. Okay, so there we go. Okay, perfect. So right now you should be seeing a white screen. You're supposed to be. I just want to do a couple math problems to show you what the heck I just talked about for the last minute because I think I was confusing you. So let's say we have something like a gram. And this is something that's in the SI unit. So let's say that we have a problem where we're given 5 grams. And it says convert this to kilograms. If you look at the chart that I had up a minute ago, which I'm going to pull up and put in this chat so you can look at it as I'm talking about this problem. The benefit of having SI units is it's very easy to convert something from grams to kilograms to decigrams to centigrams to all different types of prefixes there because all of those are just orders of magnitude. So, oh, is it not going to let me put a it's not gonna let me put. We're gonna write this. So I talked about how kilo has 1,000. Hecto means 100. And let's do centi because you've probably heard that before. Means 0.01. So when we have a term like grams that doesn't have any prefix in front of it, like kilogram or hectogram, we can easily convert it to a different form by just multiplying or dividing by a number. And all of those numbers are going to have ones and zeros in them. So I guess it's probably easier just to do a problem here. But let's say we had a problem that said, if we have 5 grams, how many kilograms do you have? So this is how in engineering, how they always have you write things. So 5 grams, like this. And as I mentioned a second ago, it's very easy to convert from grams to kilograms to decagrams. All you have to do is either divide or multiply by something of the power of 10. And right here, from what this is telling us and what that chart that I had up a minute ago that I can't send to you, but I'll send you after, is saying is that in 1 kilogram, there's 1,000 grams. So you write, I guess, the ratio between grams and kilograms here. So 1,000 grams is 1 kilogram. And then all you have to do is do the math there and do 5 divided by 1,000, and that is going to give you an answer. So 5 divided by 1,000 is 0.005. So what this math problem just showed you is that 5 grams equals 0.005 kilograms. And the reason that I'm talking about all this, and if you're confused on how the heck this is relating to anything, is that this concept is used, of unit conversions, is used in everything. So basically the whole point of this is saying that anytime you have the same units, or the same units, but just different like ways you're expressing those units, you can easily convert them in energy or in engineering conversions. So in this example is an engineering conversion. And basically you can, whatever gram or whatever amount you're given of something, if you multiply it by the ratio, you'll easily convert it to a different thing. So in this example here, I converted 5 grams into kilograms by simply just multiplying how many grams. I knew I had 5, and multiplying it by the ratio between kilograms and grams. And the thing to note here is that I started with grams, but if you have, when you're multiplying, if you have something on the top and something on the bottom, you can cancel it out. And so then you're left with kilograms. If this is confusing, I want to do one more example, and hopefully this will make more sense. So let's say we're given a problem where it says you have 10 kilograms. How many grams is this? So first, when you're doing the conversion, you start with what you're given. You're given 10 kilograms. And then you multiply it by the factor or the ratio of the two. So we know that we're given 10 kilograms and we're trying to get grams. That's the final conversion, the final thing that we want. So you multiply this 10 kilograms by the conversion factor of kilograms to grams. And what I mean by conversion factor is how many kilograms equals 1 gram. And we know, or how many grams equals 1 kilogram. And we know that ratio is just, there's 1,000 grams in 1 kilogram. No, really wants me to erase here. So why is it still trying to get me to erase? Okay. Okay, so the difference between this problem and the one that I just did is in this example, you can see that 1,000 grams, I'm multiplying it now and not dividing it. The way that I know that is because if you, whatever you want your final answer as, after you do this conversion, it should be the only thing left. And in this example, like I mentioned in the last one, if you have 2 units that are the same on the top and the bottom, you can cancel them out. So kilograms there is on the top, kilograms here is on the bottom. So now I just do 10 times 1,000, and that's going to give me 10,000. So then I know that I have 10,000 grams. Okay. I really hope this is not totally confusing you. I hope you're following me. And if you're confused as to why the heck I'm showing you this weird way of writing things when it's as simple as just multiplying it by 1,000, it's because when you're doing these complicated math problems, you should write it in this way, because for the problems in like the chapter 3 that are related to those hard math problems, you have to convert a lot of different things, not as simple as converting kilograms to grams. And so you need to make sure that your units are canceling on the top and the bottom. And that's kind of why it's so confusing. And if you don't have a background in this, if you're confused right now, it's okay, because I don't think anyone expects you to know this. This isn't supposed to be a math oriented class, but basically this concept is really important, and this idea that doing engineering conversions. So I'm gonna stop sharing this because I hope I didn't entirely confuse you for the past 10 minutes, but let's go back to this. So I think you can see my screen again. Yep. So kind of going back to this, all of these problems that are these complicated problems, the reason they're so hard is because there's a ton of conversions that they're making you do, and I really don't think they should be making you do them. A prime example is this problem right here is an exact quiz problem that you're given. And this one is really, really confusing. And the reason that I got it wrong at first is because this is the equation they give you. So P divided by A equals E, which stands for emissivity, times this weird O looking thing, which is a constant, and then T, which is temperature. I plugged everything in and they got an answer and it wasn't right. And it's because here temperature is in Kelvin and you're giving temperature in Celsius. So if you don't convert to the right unit of temperature, you're going to get the problem wrong, even if you did all the steps right. And that's why these math problems are all so challenging. It's going back to that simple math problem I just did where I converted grams to kilograms. That was easy, right? You all knew that. But in some situations, you're not going to know, like, oh, I'm supposed to convert that. I had no idea. So definitely can be challenging. So basically, like, this is it's kind of the same concept of you can convert anything that's in the same, like it's all like temperature, you can convert between Celsius, Kelvin, and Fahrenheit, and meter, and then lengths, you can convert between meters and kilometers and different things. So I guess that's the big takeaway from the math component. Just note that a lot of these complicated problems, if you've tried them, you're probably getting them right. You're just missing these little tiny things where you have to convert between different units of energy, which is a lot more complicated than units of length. So I really don't want to go through these too often, but I do kind of want to touch on this problem. So I think it's nice to kind of break down this math problem and see that it's the actual problem itself, even though it has a lot of different variables in it, it's not too complicated to understand. So for this whole unit, when talking about solar energy and when talking about the direct use of solar energy, as chapter 8 does, they talk about this a lot. So conduction, convection, and radiation, which hopefully you have a background in that. But if you don't, I'm going to kind of really quick run through the difference between all of those, because these are all very relevant to solar energy. So convection is essentially when we're transferring heat through a fluid caused by molecular motion. Conduction is the transfer of heat or electric current from one substance to another by direct contact. So the best example of conduction is like right here. As you can see, this pot's on the fire, so it's getting really, really hot. If your hand were to touch that handle, it would hurt, right? Ow, because when you touch that handle, it was really, really hot and it transferred that heat from the handle to your hand. So that's kind of an example of conduction. So it's the transfer of heat from one substance to another by direct contact. So you directly touching that handle got really, really hot, you directly touching it is a perfect example of that. So radiation is probably the most important one. You think of solar radiation, right? And that's basically the energy that's radiated by transmitted in the form of rays or waves or particles. So the best example of radiation is, I think, like this fire here. See those arrows all going out to it? Obviously, there's heat without touching the fire, right? We all know that we sit by the fire and it gets hot even though we're not standing in the fire. That's the idea of radiation. It's the fact that it's radiating energy out and you can still get warm, you can still feel that energy without having to touch the fire, right? Without having to use conduction and touch it. So obviously you could stand in the fire and that's a really quick transfer of heat, right? Using conduction, but using radiation, you can still transfer heat to your body by that concept of it being transmitted in the rays or waves of particles. So the reason I'm talking about all that is this chapter 8 that I was going to talk about this whole time and do all these math problems relates to conduction, radiation, and convection by giving different equations that are relevant to conduction, radiation, and convection, because those are all relevant terms of solar energy. So conduction, for example, in the textbook, they pull up this equation here, and it looks like a really, really complicated equation, and it can be if you don't convert the right units. For example, if they give you Fahrenheit, and in this equation they need Celsius. I mean, there's a lot of different things that you can accidentally do wrong, but basically this equation here, what it's saying is that P equals Ka times Th minus Tc over L, and then it tells you what all of these mean. So basically P stands for, if you didn't know, because this was the main thing talked about at the beginning. So P stands for the power density per unit area. P over A is power density per unit area. So if you saw that a lot in the textbook, that's what the P over A meant. So it just related to power, or basically power density per unit area is just saying how compact, or basically it's a measurement for how big that power is, which is again a complicated term that you shouldn't have to know. But P essentially is just related to power. So what this is saying here is that when we have a problem like this, you can kind of break it down. And how I would approach these math problems is maybe underlining every variable or every number you're given and then assigning it for what it is. And then you can easily do the math here. So for example, this is a problem they're given, or that they write in the textbook. So it says to calculate the power transferred through a piece of aluminum. So power transferred, right away I know, okay, so we're solving for P, because I just said P is power density. So if you underline power, you know that you're solving for P. And then it says, so it gives you how big that aluminum is. So it's 5 centimeters by 5 centimeters by 15 centimeters, which is a lot of numbers. But anytime that it's telling you a number by a number by a number, it's either giving you volume or area. In this situation, we are given the area as 5 by 5, right? Because it's saying that this aluminum piece is 5 centimeters wide by 5 centimeters length. So that is why right here they have A is 5 centimeters by 5 centimeters. So then it says when the temperature on the hot end is 100 and the cold end is 20. Well, if you go back to here, TH and TC is referring to the hot temperature and the cold temperature. So that's why they have this written here. So you know 100 is hotter than 20. So TH they put as 100, TC they put as 20, and then L is 15 centimeters. So this is a tricky problem and one that you kind of had to interpret here. And it's the fact that we're given 5 centimeters by 5 centimeters and by 15 centimeters. So what is all that telling us? So if we were to kind of draw that aluminum piece out, what this whole problem is showing you is it's back to this idea of conduction. So again, conduction is the direct transfer of heat, right? So it's when one substance is touching another substance. In this example, if you kind of read it, so it's saying that this situation is when one end of the bar is in contact with boiling water and the other is in room temperature. Okay, so we know that it's 15 centimeters long. So we have part of this aluminum in this hot boiling water and another part, if it goes 15 centimeters out of the water and into the air. So that's why one end is really hot and one end is really cold, right? Because the hot end here, that's 100 Celsius, is in the water, and then the cold end is 20 Celsius, which we know is outside of the water. So basically, kind of that's how this equation is related to conduction, and this equation is kind of calculating that power transfer, that power density, so how that power is changing from the hot end to the cold end, and it's using all these different parameters, and it makes sense that we have to consider how long that piece of aluminum is, how wide and how thick it is, how wide we have to consider the temperature when it's in the water and the temperature when it's outside the water. So basically those are kind of why all those pieces are part of it. So in this situation and in this problem, if there is one on the quiz, they gave you this equation, and then they gave you this. So it'd be your responsibility for determining what all these numbers represent in relationship to this equation, and then just simply multiplying it out as they did here. So I think the one that might have confused a lot of you is they didn't give you a K. So you read this equation and then you're like, well, I wasn't even given a K. So this is something, this K here is a thermal, it's the thermal conductivity of a material, which in the textbook, there's a chart that tells you that number. So this K here wasn't given in the problem, but it was something that you'd have to go look up in a chart. And that's something that also is very, very challenging. So that's kind of how they came up with this K, if you were wondering. So then they did all the math here and were able to do this, use this equation to calculate P is 268 W. So you can see here, they did 20,100, which is K, which is right here in the problem, times the area, right, which is this A, times the difference between the temperature, which is right here, divided by 15, which is right here, this L. And that's how they got 268. So this is just an example of the complexity and of these problems and how, you know, they look challenging, but if you break them down step by step and piece by piece, you know, there is an answer and but it can be challenging because like this example didn't have any unit conversions, but like what if they gave you area in a different unit? What if they give you area in 5 meters by 5 meters and you had to convert it to centimeters? There's a lot of different layers and elements that can be challenging for these problems. So yeah, I guess we're running out of time. That was a quick meeting and I know a lot of it was probably confusing. So don't worry if like that this last half where I talked about this and all of that was confusing. I really just wanted to kind of give you a baseline of, you know, this is probably hard for you if this idea of energy or engineering conversions is not something you have background in, and that is totally fair. So don't worry, you know, just kind of note the main ideas I want you to get away are the solar energy, the pros and the cons, you know, maybe understanding convection, conduction, and radiation and the importance of those. But yeah, so like I said, give me this weekend. I appreciate you all being on, you know, give me this weekend. I will talk to my supervisor. Hopefully he'll get back to me by then. And then I'm going to send you all an email for how we're going to do this course. I think the best way is I'm going to probably send you a list of what I'm assuming my supervisor will say is I'm just going to tell you what problems in the quizzes to do, right? So, and they aren't going to include these complicated math problems. So they're only going to include the ones that relate to what we talk about. So hopefully that's fair to all of you. You know, let me know if it's not, but I'm hoping. So yeah, so with that, you're free to go unless you have any other questions. Just please look out for my email that will come this weekend with an explanation for how to carry on with this course. And of course, if you want to just do the math problems and tackle it that way, you can, but I don't want you to put in all too much work for it.
Can you send me a copy of your PowerPoint?
Yeah, this one?
Yeah, the one.
Yeah,
you
of
were
course.
just
I
showing
would
us.
happy to send you that. And then I also, just so you know, I think one of these is a really interesting one to look at. The kind of, this is just where I got this. But one of them is interesting to just look at. But there's a lot of different viewpoints and different like solar panel readings that you can do. So if you ever are curious, let me know. I can send some your way. But yep, I will send this PowerPoint over. And like I said, this weekend you will hear from me too on what to do. But for now, for this course, I would recommend reading chapter I think what is that, 8 and 9 or whatever the one is it's next. I know most of you already did the quiz 3, so that's why I didn't really touch on that. So I touched on quiz 8 and 9, which is over solar energy. So if you haven't done quiz 3, do quiz 3 and do quiz 8 and 9 because that's the one that's next. And then just skip the math questions for now because I'm not going to make you do all those math problems, but I will send you an email this weekend with an explanation for how it's going to work.
I just want to inform you that for the videos for chapter 8, the trade secrets solar hot water system video is non-accessible because it doesn't exist anymore.
Oh, well, that's not good. That's fine. I don't think that one was too, I didn't watch that one either. Well, I guess I didn't watch it because I couldn't. Don't worry about that one. I wouldn't worry too much about the videos. Maybe I'll send a list too of the videos that are helpful for you to watch.
Because I had a question for it in the video discussion stuff, and I was just trying to answer it.
Yeah, you don't have to do the video discussions, just so you know. Those aren't part of you're not graded for the video discussions.
Okay. Well,
Yeah, I don't even watch the videos, so I just read the book.
Yeah, I think the book's probably more helpful. Except it's so much of it's heavy in math but yeah.
All right, thank you.
Yeah,
Have a
of
good
course.
night.
Thanks, you too. Hi, Courtney. Do you have any questions left?
No, I don't think my computer's letting me leave.
I think there's an end in the right corner. You hit that, it'll X you
Well,
out.
it says leave and I'm clicking on it. It's not letting me leave. So.